I'm going to calculate the pH of this solution. Suppose that 0.0200 moles of sodium hydroxide is dissolved in 300 milliliters of the following solution: 0.40 molar sodium acetate and 0.08 molar acetic acid. What's the final pH of the solution? Before we determine the final pH of the solution, let's determine the pH of the solution in the absence of the added sodium hydroxide. What you want to do is recognize that there's a substantial amount of sodium acetate and acetic acid, conjugate acid-base partners. In this case, I know that this particular solution is going to behave as a buffer. So I'm going to use the Henderson-Hasselbalch equation as a shortcut to determine the pH of this solution. The Henderson-Hasselbalch equation is the pH of the solution plus the pKa of the solution, or equals the pKa of the solution, plus the log of the concentration of the anion of the acid divided by the concentration of the acid. In this case, it's the initial concentration in the solution of each. So when I plug those numbers in, I get that the pH equals the pKa, and the pKa I can look up, or I can calculate from the Ka to be 4.75 plus the log of the concentration of the salt, which is 0.04, divided by the concentration of the base, which is 0.08. So in this case, for this particular solution, before any added sodium hydroxide, the pH is 4.45. Okay? Alright, now let's consider this solution after the addition of the 0.0200 mole of sodium hydroxide. This particular part we're going to have to solve in two steps. First, we're going to have to recognize that the sodium hydroxide is a strong base, and it's going to react to completion, if possible, with the acid in the acetic buffer. So first we write the neutralization reaction to determine the new starting concentrations of the acid and base in this particular solution. Okay, so first we're going to do the neutralization. So I said that the sodium hydroxide would react with the acetic acid. So the acetic acid in the solution is going to react completely with the sodium hydroxide in the solution to give sodium acetate and water. Okay, so essentially what's happening here, if you think about it, is you have this solution originally that has acetic acid, a substantial amount, and the acetate anion, a substantial amount. We're going to add to this solution the sodium hydroxide, and we're going to calculate the new concentrations of the acetic acid and the sodium acetate. Alright, so we have a total of 300 milliliters here. So to do the neutralization equation, I have to figure out how many moles of each of these compounds that are already in solution before I add the sodium hydroxide. So for the acetic acid, the concentration is 0.08 molar. So I'm looking for the number of moles of acetic acid here. So the concentration is 0.08. I'm going to multiply by molar, multiply by the volume, and I'm going to get the number of moles. In this case, it's 0.024 moles floating around in that 300 milliliters. And then the moles of acetate that are already there, we have 0.04 moles, or molar, floating around in 0.3 liters. So the acetate, we have 0.012 moles floating around in there. Okay, so that's what we have in the solution already floating around, the acetate and the acetic acids. Now we can go back to the neutralization equation and say, okay, initially I start off with 0.024 moles of the acetic acid. I'm adding to that 0.02 moles of sodium hydroxide. I already have in solution to start off with 0.012 moles of the acetate ion. So the change then, since this reaction goes to completion, the limiting reagent is the sodium hydroxide. So I'm going to react away all of those moles of sodium hydroxide, and I'm going to create, with the combination, an additional 0.02 moles of the acetate, and of course the water we don't consider. So at the end of this reaction, I'm going to end up with 0.004 moles of the acetic acid, no moles of the strong base sodium hydroxide, and 0.032 moles of the acetate. Okay, so now the next part of the calculation is I have to consider what's in my equilibrium situation again. And since I have a substantial amount of acetic acid and a substantial amount of acetate, I know that this particular solution is going to act like a buffer. So I can calculate the pH, because I have both of these present, using the Henderson-Hasselbalch equation to calculate the pH. Now, in order to do this, I need to have the concentrations of each of these components, not just the number of moles. So I need to determine the concentration of the acetic acid now. Okay. Its new concentration is going to be 0.004 moles divided by 0.3 liters, because it's still in the same container. And that concentration is 0.013 molar. The acetate is 0.032 moles in the 0.3 liters, and that concentration is 0.107 molar. Okay, so with those two concentrations, I can use the Henderson-Hasselbalch equation rather than going through the entire equilibrium. As a shortcut, log of the anion over the acid. So the pH equals 4.75 plus the log of the anion, which is now up to 1.107, divided by the acids down to 0.013, excuse me. And when you calculate the pH here, the pH is now up to 5.65. So I'm almost outside the range of the buffering capacity, because I've almost used up all of the available acid to react with the added base.